Homework 3 is due tonight, correct?
Yes.
Okay, that's two-dimensional trajectory motion, correct? We better get going, right?
Yes.
You'll notice that the key to the review packet is out there on the wall.
Oh, you know what's funny? Yesterday I found the junior
Two-dimensional motion. That's one we'll study a little bit later. The one we're going to study about, by the way, the difference between, say, projectile motion.
Projectile, I couldn't remember what it was called.
Projectile and circular. The difference between the two is the direction of the force. The force. May the force be with you.
He's one
The force is strong in this one.
math class, yes.
All right. Here we go. The difference is how the force behaves. In circular motion, which way is the force on the object? Always towards the center. So the force, F, is always pointing towards the center. And as the object moves forward and turns, the force turns with it, so that the velocity vector and the force vector are always perpendicular. Remember that from last year? Okay, if it's uniform circular motion, UCM, okay, then it will go in a perfect circle, no speeding up, no slowing down. Kinetic energy remains constant, no work being done, okay? Now this particular type of motion, the velocity, remember, is always tangent to the path. Okay? But the force, on the other hand, in this particular type of motion, which is parabolic, is a type of force that never changes direction. Okay? In this case, the force remains in a uniform direction. So the force is downward in this case. Now the force does not have to always be downward to produce projectile motion. You could produce projectile motion like this. But which way is the force in that case? Upward. Now that seems kind of weird because we're used to seeing projectile motion like this because of gravity. We see this all the time in daily life. Any ball sport, any kind of sport where the object flies through the air, like the long jump, or gymnastics, or basketball, or baseball, or football, all projectile motion, all parabolic, assuming there's not a lot of wind resistance, right? Air resistance. Okay, but we see this all the time in nature, particularly if we have something like this.
Oh dear. Are you doing a monkey thing? Why is
Okay,
everyone?
what kind of charged particle is moving through there?
A positive.
A positive charged
I
object.
can't handle this.
You have a positive object right here. And the positive object is getting an electric force this way. And it is exactly the same motion. It's parabolic trajectory motion. It just flipped upside down. That can be in any direction, right? If there is a static electric field that's uniform, then you're going to get a uniform force, and you're going to get parabolic trajectory motion. Okay? Or projectile motion. Anyway, it's the same thing. There you go. All right. So let's skip circular. We're not going to talk about that right now. Just our tie into electrical when we get there, because this can happen, and you will see this.
Oh, but it's gone for now.
It will happen. Just not right now.
I don't see it. It doesn't exist.
That's right.
Out of
I don't
sight, out of
believe in it.
mind.
It doesn't exist.
Out of sight, out of mind. All right. Excuse me. Okay, here you go. By the way, don't forget, velocity always tangents to the path, always tangents to the path, always tangents to the path. Right? Okay. All right. So here we go. What projectile motion then is look, if the force is down, then which way is the object accelerating?
Down.
Down. That means the acceleration is down, and the acceleration for us in a gravity field is g. Right?
Yes.
So what's the acceleration in the x direction?
0.
There is zero.
There is none. That means that the x velocity never changes. The x velocity should stay exactly the same the entire time. Okay, important thing to note, at the top of projectile trajectory motion, there is no y velocity because it stopped going up, but there still is x velocity, right? It's still moving. The x velocity at the top is the same as the x velocity anyway. All right, the y velocity, on the other hand, is changing because of acceleration. The y velocity is up, it's less. Y velocity is 0 at the top, y velocity is down, y velocity gets bigger downward, okay? The y velocity is changing. So, let's see, let's make sure we've covered everything. It's parabolic, it's symmetric. The right side and the left side are all the same, right?
Mhm.
That means it takes the same amount of time for it to get from here to here as it does from here to here, as long as they're talking about the same height. Okay? Blah, 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 got that. Y velocity at the top is 0. All right, which gives us this, everyone. That in the x direction, it's quite boring and quite simple. Because we have all these equations. X equals x naught plus v naught t plus 1/2 at squared. And let's just look at that equation. What's the acceleration in the x direction? None. If we say we start here at 0, then that's 0. And what we end up with is this equation, x equals v naught times t. All right? So that's a useful equation. But our other two equations, v equals v naught plus at, that doesn't tell us anything in the x direction, except since our acceleration is 0, it tells us that the velocity doesn't change. And our third equation, the v squared equation, tells us the same thing, that the velocity squared final equals the velocity squared initial, because the acceleration component falls out. All right? So our velocity remains constant. So in the x direction, that's all we have. Very simple. In the y direction, it's a tad bit more exciting. In the y direction, we have these three equations. Because there is an acceleration in the y direction, which equals g downward. Now, I didn't make that positive or negative because you can decide whether you want to have up positive or down positive. In some cases, down positive is mathematically simpler, but in most cases, you'll pick down as negative and up as positive. Okay, y equals y naught plus v y naught t plus 1/2 ay t squared. And for us, this ay is going to be g, right? So I'm just going to change that to g. All right, so we have that one. And then we have vy equals vy naught t plus 1, vy naught plus gt. And we also have vy squared equals vy naught squared plus 2g y minus y naught. Did I get all those right?
Yes.
All I did was substitute a y in. To remind us that we're talking in the y direction, correct? All right, so that's it. We have these three equations, which we already know about, in the y direction. But in the x direction, really all we have is this one. Nice and simple. Nice and sweet. Simple, 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 simple. Okay. Now, all trajectory problems break down into three major categories. Easy, a little bit tougher, and then
Monkey.
and then monkey. No. Then, like every other problem, the hardest ones. Okay, they look like this. Here's problem number 1. So that you remember it, it's called car driving off cliff. Okay, this is number 1. Problem number 1 is car driving off cliff. Okay, what part of this trajectory is it?
The halfway.
It's from here down to here, right? It's the back half of the parabola. And why is this one a little bit simpler? Because your initial y velocity is 0. Since your initial y velocity is 0, vy naught equals 0. that makes this equation here into this. And then it also allows you to call down as positive. This is the one case where down being positive is kind of convenient. If you call down positive, then you could say it starts at 0 and it lands at y, where y will be the height. So these two will be 0. So that's 0 and that's 0, and call down positive, and what you end up with then in the y direction is y equals, or the height of the cliff equals 1/2 gt squared. And this is where we get that nice simple equation, which we call the time to fall equation. T equals 2h over g square root. Now, that's the time to fall only if you drop something. Notice the car is dropping in the y direction with no initial velocity, right? So this equation is good for this, right here. And it's also good for this. That's it. It's not good for this or for that. Oh, I broke that. Okay? All right.
Oh, okay.
So there you go.
Oh, okay, yeah, sure.
So case number 1.
Sure, no problem.
All right, case number 2 is the cannonball problem. You have a cannonball or a cannon, and you shoot a cannonball out, and it launches and lands at the same height. Okay? Sometimes called the range problem. Okay? Launch and land at the same height. There turns out to be a, well, the reason why this is almost as simple, yes.
Can I ask a quick question
Sure.
on the first one? You know how sometimes they ask like how far from the cliff
Yes.
does it fall?
Mhm.
Is that just x equals VOT?
That's that.
Okay.
That's correct. Very nice.
Okay, just wanted to.
In fact, in every one of these, in the x direction, it's x
That
equals
works for all of
v
them?
times t.
Yay.
In every one of these, the x is the easy part. Okay? There's a trick with this one if you'd like. You could just split it in half and solve this part is right here and then just double it, right? You could do that. There turns out to be a special equation for this one, which we'll talk about in a little while. But the nice thing about this one is it's symmetrical. So the launch velocity over here is the same as the hit the ground velocity over here. That one and that one are the same. Okay? They're exactly the same.
The initial and final.
The initial and final y velocities are the same, but in the opposite direction. And so, since the x is the same at all times, the total velocity will be the same at launch and land, but they'll just be pointing in different directions. It will come back to you. You've seen it twice already. And so, if you didn't get it the first time, which most students don't, and you kind of sort of get it the second time, you'll get it this time. I promise. And if you don't,
You get almost this time.
you'll get it. All right, so there you go. And our last type of problem is this one. It's the random type problem where you launch something and it lands at a different height. Okay? It's going to be called the basketball shot. You're shooting a basketball towards the goal. You're at some height. The goal's at a different height. So there's no special way to get around any kind of symmetry or anything. There's no special symmetry that helps you out, okay? Or it could be the other one like, I call this one the Santa sliding off the roof problem, okay? Santa's on the roof, he slips, he falls, and he slides off the roof like this. So he launches down at a down angle, and he lands somewhere else, okay?
Isn't that the same thing as number 1 though?
No, it's not. Why is this one different than that one?
It's not going off the last.
Yeah, because the initial y velocity is not 0. So you don't get to do this. All right, in this problem right here and in this problem, you really must call up positive. Well, you don't have to, I mean, if you don't want to, you can be stubborn and call down positive, but then that means if you get a positive y velocity, that means down, and negative means up, and that just messes with your brain. So I suggest you call up positive. That means g is going to be negative in both of these. Okay? All right. Let's work a few of these problems. Let's do a horizontal launch, then we'll work our way to the more difficult ones. All right, let's say that you're on a parking garage and you're drag racing. Unfortunately, you can't stop in time, and you drive off the top of the parking garage at 45 meters per second, which is approximately 100 miles an hour. Okay, and you're 20 meters up. So what's that? That's about 60 feet. So it's a 6-story parking garage. All right. I want to know a couple things. Number one is where does the fire department need to scrape you off the ground? So where do you hit? So where is X marks the spot of your demise? Second thing is I want to know how long do you have to, make amends with your maker before you go from here to here. So how long does it take you to hit the ground? And time is relative. In this case, time is finite. And how much time? Time to hit, and where do you hit? And then I want to know, at what velocity do you hit?
Oh, man.
There you go, those three things,
Okay,
and
so
go.
You want the distance, the time, and the...
That's correct. How far away from the parking garage do you need to put your tombstone? First intelligent thing, well, maybe not the first. An intelligent question is, this velocity that was given, is that what kind of velocity? That's an x velocity. Very good.
Okay.
So what's the y velocity?
0.
The initial y velocity is 0. Will the y velocity here be 0?
So what we're solving for is the final y velocity?
Okay.
Velocity
So
total.
here's the deal. Is you're going to have 45 meters per second here. Will that 45 meters per second reappear here?
Yeah. Part of it.
As what part of the velocity?
X.
Okay, the x part of the velocity is still going to be 45, but the y part of the velocity will be something else.
The same.
Yeah, because the x stays the same,
So
because there's
we're
no
solving-
acceleration.
So we're solving for the y velocity.
So you'll solve for the y, but did I ask for the y velocity?
What did you
I asked for the
No.
velocity that you hit the ground at. So what's the velocity that you hit the ground at? Is that x or y?
Oh, why?
It is the velocity, which is x plus y.
49.
93.
49.
So that's this velocity.
49.
Okay. Okay.
49.
So I want to know what the hit the ground velocity is.
Not done with my question.
Oh man, my voice is getting
Okay. So for the
I just hit puberty.
okay. So for the y
Pretty
velocity.
sad.
Finally.
The final y
That's
velocity,
it,
all you do is do gravity times time.
Yes.
Okay.
That's correct, because it would be v equals v naught plus at, but the initial y velocity is 0. That's correct. Very good.
Y velocity?
I got 49. Did you get 49?
You could.
Okay,
Be careful though. Because when you start with no initial kinetic,
divided by 10, it's 20, so
we start with kinetic and end up with kinetic.
20 meters.
You only found
equal to 1/2 AT
You didn't set
squared.
that up right. Because there's that kinetic. You start. That's fake. All right, I just made this problem up, so I don't know what the answers are, but I'm pretty sure that the time to fall
About 2 seconds.
It's
2.2.
7 seconds.
What?
Seven.
Stop it, Andy.
Don't listen to Andy, Oscar.
Yeah, that was.
Andy just makes up numbers.
But yes, I do make up numbers, but the funny thing is, Bruin listens to me every time.
It's because I'm a believing, caring soul. And I'm not cold-hearted like you are. All right, here you go, everybody. This equation right here is not on your equation sheet. So you need to know how to derive it. Remember, the time to fall is this. Starting at 0, calling down positive. You start with a 0 y velocity. So this is the height that you fall from, 1/2 gt squared. So this is 20 meters. That's 1/2 9.8 t squared, which is the same thing as you get over there. The time to fall, I believe, is 2 seconds, correct?
Yes.
All right, 2 seconds to hit the ground. All right, in 2 seconds, how far will you have gone? Okay, in 2 seconds, x equals v times t, and that's 45 times 2, so you'll go about 90 meters. Piece of cake. Here you go, problem number 2.
No.
All right, once again, I want to know the time it takes for this object to launch, from launch to land. I want to know the time. I want to know the x distance. And I also want to know the max height.
Oh, this is like number 5 on our homework. It was asked for so much. Is it
I
bad?
know, I'm very demanding. I'm
Yeah.
high maintenance.
Number 5. Number 5.
There you go. Hey, when we have a problem like this, absolutely positively, even if they don't ask for it, what's the absolute first thing we have to do? Separate your velocity into x and y. Because we're making this problem into something we can solve by simplifying it into parts, into 2 things that we can think about. We can think about x, we can do okay with x, we can do okay with y. We can't do okay with both of them at the same time. So, separate it into x and to y. And quite frankly, if you separate it into x, magically you've got some cool stuff already, right? Here's 24. Take advantage of your special triangle. If this is 24 meters per second, what's the initial y velocity? 12 meters per second. What's the x velocity then?
Oh, we already know that.
12 times the square root of 3, which is
20.7.
20.7?
20.78.
Okay, 20.8. There you go. And we almost answered one of the problems already then, didn't we?
Yeah.
Come on, you're not doing anything I haven't done already. Very slow. Right, here's the deal. A lot of times we don't know whether we find time in x or y. Because remember, when we do these problems, we keep our x and y stuff completely segregated, right? They have to be separate because x stuff is x stuff and y stuff is y stuff. But time appears in both columns, right? The time transfers between the two. So we could find time in x and we could find time in y. In x, if we can find time, it's the easiest thing to do because it's just x equals v xt, right? Over here we have those 3 equations. So do we have enough information to find time this way?
No.
Drat, we don't know x. So all we know is this. We know that x equals 20.8 t. All right, so let's go over here. What do we know in the y direction? We know our initial y velocity is 12. Positive. Can you tell me what your landing velocity is? No. Negative 12. Very good. Why is it negative 12?
Because they go the same.
Because it's symmetric, right? And you're at the same height. And you can also argue it from conservation of energy. It has to be going the same speed at the same height, right? Okay, so we know that. Do we know the launch position? Do we know the landing position? Do we know the acceleration?
Negative 9.8.
Negative.
Thank you. Negative. We know everything.
Except for time.
Everything but time. So you can find time from y equals y naught and all that. Or you could just do it from this one. V equals V naught plus AT.
That'll give you half.
Where this is minus 12 equals 12 minus 9.8 T. So what's T?
4 over 9.
So the whole time.
2.45?
Yeah. Yes.
Or about 2.5 seconds? Okay, there's my time. You can take time, plug it in here, and find x. X then equals.
X then 50.9.
About 51?
Yeah.
Alright, by the way, this is not the only way to solve for time. If you want to solve for time with the y equals y naught plus all that, you could solve it that way, but it turns out to be a quadratic, right?
Yes. But one time will be 0.
Yes. Does one time turn out to be 0?
Yeah, you can actually.
Oh yeah, it will. One of them 0 because it starts at 0 time. Yeah, at that height. That's correct. So it's quadratic, so you could solve it either by graphing out of the quadratic formula, whichever. It doesn't matter. This turns out to be easier. Either one's right. Okay, max height. Now here's where we have to be careful, everybody.
Divide by 2.
Okay, max height is not here. Everything we've done so far is for here. So please be careful. We're looking at this spot now. So there are multiple ways to do this. A lot of students like to just chop the thing in half and take the time and cut it in half and then find the height by doing something like y equals y naught plus v y naught t plus 1/2 gt squared, where it starts at 0. So y equals, starts with what, 12, is that right? Times 2.45 divided by 2 for your time, plus 1/2, 9.8. Uh-oh, I made a mistake. What did I do?
Negative.
Okay, this is going to be negative. You'll save a lot of time if you realize that's negative 4.9. And then 2.45 over 2 squared. So that will give you your max height. That is not the only way to work that. You could solve this with the v squared equation. That will also work. Because what's the velocity, y velocity at the top?
0.
0. So you could do the v squared equation if you'd like, and it would solve for the distance directly without having to use time. It doesn't matter. 7.35 meters. Voila, done. Okay. Now let me show you a special equation that shows up just for this particular type of problem. It's called the range equation. Let me show you how it is derived. Okay?
This is a cool equation. Why don't they put it on the
Yeah, it is not on our equation sheet, unfortunately.
4K?
All right, here we go.
Angie wants it.
Does everybody agree that the range Does everybody agree that this is true? That the
Yes.
range from here to here will be x, which is vx times t.
Yes.
Okay, but vx is actually going to be
V of.
v cosine of the angle times t, right?
Yes.
Okay, so we got that going for us. All right, now, we also have this. Does everybody agree that from here to here, the time is going to be 2h over g square root?
Yes. Yeah.
Okay? I don't like that. That's not going to help us. All right, let's do this instead. Let's go back to our time right here. Does everybody agree that right here, v equals v naught plus at, the same way that we found the time right here? Okay? But our v naught and our v, that's really just v sine theta, because this is the y dimension, right? Minus gt over here equals v sine theta here, but this one's negative. Does everybody agree with that?
Yes.
Because this launch velocity and the landing velocity are the same, but the landing velocity is negative. That's correct. So this turns out to be that t equals 2 sine theta over g. Is everybody okay with that?
Yes.
Wait for it.
Yes.
Wait for it.
Oh, yeah.
Got it? I'm going to take this, I'm going to plug in here, which is going to give us x equals v cosine theta.
Mr. Bruin.
Yes.
Using a B at
Negative
2 B.
No, don't it be?
Oh, yeah.
Okay.
Thank you. I'm missing a v. Thank you.
Oh, I know he subtracted them.
I moved this one over here and this one over here. So I added this one over here, added this over here, and I divided by g. Thank you. This is why I always ask you to check, because I'll make mistakes. All right, so that's that equation, but t is equal to this. So t is 2v sine theta over g. All right, that's the same as 2v squared cosine theta sine theta over g. You know what, I'm going to rewrite that a little bit different. 2 sine theta cosine theta. The reason why I'm writing it that way is 2 sine theta cosine theta means something. Oh, you remember. Because I never remembered that one.
Sine
Man, sine 2 theta over g.
Yay.
And this is for the, this is number 7.
Okay, now this is for the range. It's called the range equation.
Looks very nice.
It is the x distance if you launch and land at the same height, assuming no air resistance, right?
And now that we learned that formula, we're going to get all either air resistance or things.
Oh, so you
That's
can
correct.
make it 5.
What angle do you need to launch according to this to get maximum range?
Okay, I need to observe.
45.
The sine is anywhere from 0 to 1. To get maximum range, you want 1. Sine of 90 is 1, so 40. You need a 45-degree angle there. 45 times 2 is 90. Sine of 90 is 1. Okay? So in theory, no air resistance. If you launch something at a 45-degree angle, it will go as far as possible. That means that if you launch it at a higher angle than 45 or less than 45, it will go at a shorter range. And there are, in theory, then 2 angles that you can launch something and it lands at the same spot. Okay? If you play golf, you understand this. Here's the green. Here's the pin. There's the hole.
Wow, that's a good drawing.
You're here. You can hit the hole by doing this or by doing this. Which is better for golf?
Top one.
No, the lower one's bad because it keeps going.
Top one.
The top one's good. Why is the top one better?
Because it has less.
Talk to me in physics.
Less
Less x velocity. So when it hits, it won't roll very far, right?
No.
That's why you approach the green like this and not like this. And plus, if you hit it right, you put backspin on it, it hits and stays. If you're really good, it hits and goes backwards.
Or if
like
you're
me,
really
you hit it
good,
like this.
you hit it and it lands in the hole.
Yeah, if you're really good, it lands in the hole. It's in the hole. Hometown boy, tear his eye, I guess. By the way, the 2 angles that will hit the same spot will be the angles that both add to 90. So like you hit it at 60 and 30. 60, 30, add to 90. They'll both hit at the same spot. 80 and 10 degree angle will hit the same spot. 40 and 50 will hit at the same spot. Now, in the real world, and this is important for like if you're throwing a javelin in the Olympics, 45 will not get you a gold medal. For a javelin, it's somewhere down around 30 degrees, 30, 35 if I remember correctly. Because there's air resistance. And if you have air resistance, you need to put more x velocity into it because air resistance cuts your x velocity. So you need to put as much into it as possible. But you still need to angle it up so it has some loft to it. It stays in the air longer. So it's the more air resistance, the lower the angle to get maximum range.
The javelin spinning this way.
The javelin, yeah, it rotates like a football when you throw it to give it stability. Because otherwise, if you just like throw a knuckle, it will turn sideways. Okay, so there you go. There's the range equation. This is not on your equation sheet. It's not necessary to ever solve a problem, but if you ever have a problem where you need to know the range, it comes in handy.
Like e-homework.
Like e-homework. There's a couple problems, I think, in range equation. It's really nice.
5 through 7.
5 through 7?
Yeah.
Because they give you the range and the angle.
Oh yeah, that makes it really easy, doesn't it?
Yeah, you need to solve
If
it.
you solve it the other way, it's really hard.
Yeah, there's a lot of substituting for it. You're right, so you had to be on. All I need is 10 and 11.
This is still negative, right?
You throw it up and
So glad I'm not. Oh, no.
That's not true.
And we don't get those.
But it does help.
There you go.
Nice thinking.
Free throw shot. By the way, that's approximately correct. 15 feet to the hoop, 10 feet up. And so in meters, that's what a free throw shot looks like. And I'm assuming a 6-foot person. So this is like 6 feet off the ground. All right? The person launches the ball at that velocity, at that angle. Here's what I want to know. Does he make the basket?
No.
that's it.
Yes.
Sounds
familiar.
It bounces off the rim.
And then I want to know if he doesn't make the basket. Wait a minute, I said he. That doesn't necessarily have to be a boy.
It's a chica.
Oh, this is good. No.
What are the balls like? It changes mine halfway to the drawing.
All right, now wait a minute. I said does he make the basket, and the girl said no. Now, does she make the basket?
Oh,
Yes.
of course
She's
not.
supposed to say yes.
I'm psychic though, so I already told you.
All right. Does she make the basket? Yes or no? And then I want to know. Well, just answer that question first. Yes or no? It's the very first thing you do when you launch at an angle.
Split.
Draw the
Split it.
Draw the square with the phone.
That's all I see.
Say a prayer.
Give it. He missed it.
This time we have the range.
Oh, okay. So, and then you use that.
Range divided by
Yeah.
Then I have my time.
Or you can put 1.2 meters.
And you use it.
To both of you.
Oh. Go ahead and answer my whole.
I say she doesn't make it. Right.
Okay,
We're
is
trying.
that the next step?
Well, once you have the time, you want to see at what height the ball is at that time, right? That's where it's going to be in the basket, X-wise. So if the height is 3, then you'll know that.
How long does it take the ball to get to the basket?
0.73 seconds.
0.73.
What?
3.732. I think she's gonna throw it over the basket.
She missed by a little bit.
What?
Yep, see, I told you. Oh, no, yelling.
Sorry.
Okay.
All right, so it takes the ball, since we have enough information in the X direction, we can solve it for the time it takes the ball to get there. And then we can tell how high the ball goes.
Okay, that's 3.
And there are several ways to do this. The nice thing about this equation is you can put in the initial height and the final height. Now, some of you have figured out it's 1.2 meters here, and you're assuming that the ball starts at 0 and it goes to a height of 1.2 is what you're looking for. That's fine. what I did instead was to do this. I said it starts at 1.8. And then I'm gonna see if it lands at 3. Okay, same thing. This velocity is what? 8.2 sine of 40 times a time of 0.73 minus 4.9, 0.73 seconds squared. And when I did mine, I got 3.
I got 2.03.
Yeah, I got like something like 3.03 or something like that.
Yeah. So does she miss?
So what does that mean?
And so how far is 3? How far is
0.03.
0.03?
12. I mean, 1
That's
inch.
3
An
what?
inch.
That's 3 centimeters. That's an inch difference. I call that a basket.
I caught it
I
off.
have a question. Okay, you're saying that 3 meters is from the bottom to the bottom of the goal.
Two.
But then then the actual rim is even higher, so maybe you
No,
like
no,
the
no,
net
no.
of
The 3 meters is to the hoop. It's 10 feet from the floor to the rim.
Oh, Miss Bruin, you know what you could do? You could say the 4.6 meters is to the center of the rim, and then you can give the rim a
Because
radius.
the 4.6 or the 15 feet is to the backboard, right? Or it's not to the middle of the hoop, is it?
Well, it should be, otherwise.
I think it's to the backboard. I think the hoop
Then you
sticks
don't
out a
know
little
if
bit.
it makes it.
We'll call it close enough. We'll
Close enough.
proclaim victory. All right, here's, what's that? No, the ball does not start at rest. Okay? All right, everybody, when we have a problem like this, it's highly likely that they may not give you this distance, and therefore to find time, we have to work through like this equation backwards. We would know the launch height, we would know, say, like the landing height, we would know the velocity and g, and then we'd have a quadratic. Don't let a quadratic disturb you. It's possible that we could end up with a quadratic. Just graph the darn thing and look for the roots. Or do the quadratic formula, right? So if they give you one that you need, that you cannot find the time in the x direction, you're going to end up with a quadratic in this particular problem. Okay, no big deal. Quadratic formula or graph it and find the roots. Yes?
Can we just say the magic K?
The what?
The magic K.
Yes, what you can do is you can say from my calculator or from the quadratic solver or TI-89 gives me this. Now I'll tell you that a lot of these problems, like if it requires calculus, you'll need to show your steps. Okay, so don't just write the answer down because you'll miss points in the middle. Okay, so on this one it's fine.
If they were to give you this on the AP as a previous class, what would they count as making a basket?
Oh, they won't be that vague.
Oh, they would say?
They won't. This is kind of a vague problem.
Okay.
Okay. That's why the questions are so contrived and worded so weird, so that students hopefully cannot misinterpret what they want. But that means that you end up with a paragraph at the beginning explaining the problem, right? All right, one last thing I want you to do for me, please. Everybody, I want to know the velocity at the basket. The same. That's what, 6 point what?
6.28.
What did they exclude?
All right, what is it?
Negative 1.9.
1.9? Okay, now wait a minute. It's negative, right? There you go, done. Ah,
Hey, mini back.
buddy, get out the magical blue sheet of paper from yesterday, or from Tuesday.
Oh, wait, we supposed to do that?
You didn't do that?
You didn't really say.
Andy, put your name on it. Turn it in. Andy's gonna collect them for everybody.
Are you on this thing for one? Not today, next week, right? It depends on the-
All right, we have 2 things left to do. Number 1 is that magical blue sheet of paper. And number 2 is that
You
we
just
talk
said
about
you
our
have 2 things
exam.
to do. Number 2 is, and then you said number 2.
Let's go to this side first. Everyone, Quiet. This side first.
Oh, the other side first? Oh, that
This
side.
side. All right. Quiet, please. My voice is going. Particle moves along parabola with the equation given by y equals 1fx squared, as shown. Suppose the particle moves. Hey. Suppose the particle moves so that the x component of its velocity is constant, where vx equals c, where x equals ct. All right, on the diagram to the right, indicate the direction of the velocity vector and the acceleration vector and label them at point R. Will you do that for me, please? Which way is the velocity vector and which way is the acceleration vector?
Physics bird.
Okay, you better get velocity right. Which way's velocity?
That way, tangent.
Okay,
To the curve.
tangent, but is it tangent that way or this way?
That way.
Why?
The way it's going.
Because of the motion of the particle.
It's positive.
Because you notice x equals ct, and as time goes by, it's going to be moving to the right, correct?
Yes.
Okay, so velocity will be tangent. Velocity is always tangent to the path. Now, which way is the acceleration?
Straight up.
Why straight up?
Because velocity is constant.
Velocity is constant in the x direction, but it is a curved path, so therefore it must be accelerating. So therefore the acceleration has to be this way. The acceleration is only in the y direction because it says the x velocity is constant. There you go. I think you got 2 points. Okay, now it says determine the y component of the particle's velocity as a function of time. Bummer. As a function of x.
Should that be time? Or
No. So here's our problem. Velocity equals dy dt. Here's the way I solved it, because it wants me to ask for the velocity in the y direction as a function of x. Well, I know this, right? And I know that Vy equals, I know that y equals 1/2 x squared. But what's x?
CT.
So it's 1/2 c squared t squared, right? If I take the derivative of that, then what do I get?
You
You get
get
4
c squared
CT.
t.
I get
He does what?
Yeah, it is.
1/2
Constant.
c squared 2t.
Plus.
So I get c squared t. But I want that as a function of x. But I know that x equals ct. So this is the same thing as c times ct, right? It's the same thing as c times x.
No.
Yes.
Oh, yeah.
And done.
Well, wait.
So that's the.
Yes. This is the calculus that can cause us pain, right?
Oh, I see why.
Now, let's see if we can solve that another way.
Okay, this is just.
Yes, I'm positive that's the answer.
Well, since he is like the key, I'll figure.
Why would?
Wait, why is it 1/2 c?
Wait, where did that whole x equals CT come from?
It's given.
Problem.
It's given.
Oh.
So I tried.
Sorry.
Yes.
Let's walk through it.
Okay, here, did you do this?
X equals C. Because that's not a function of time.
I hate these very
Okay, everybody, follow me here. I'm not sure if this is going to work, but it just came to me, so let's see if it works. dy dt is the same thing as dy dt times dx. dx. What's dx over dx? 1. But I can put dx down here and put dx up there and rearrange it, right?
Yes.
Okay, what's dy dx?
Oh.
That is 1/2 x squared. What if I take the derivative of that with respect to x? What do I get?
X.
X. Oh wait,
Okay.
yeah. 2 over 2
What's
x.
what's x? It's ct. What if I take the derivative of that with respect to t? I get c. Voila, done.
Yeah. Oh, okay. Because the other one, you can't just take the derivative and then plug in x, right? Because it's not a function.
That was really cool.
Wait, yes.
What happened?
Can we do that again except slower?
Okay.
Sounds like a.
That makes perfect sense.
I caught it all the way up to the dy
Okay, dy dt, and I can do this, right? Because anything multiplied by 1 is the same thing. And so all I'm doing then is taking dy dx, I'm just rearranging this, dy dx times dx dt.
Yeah, okay.
Okay? So y equals this, x equals this. So I take the derivative of this with respect to x, which is x.
I think you should frame it.
And I take the derivative of this with respect to t, which is this, and I multiply them together, and I get xc,
That was cool.
which is nice. Yes.
Well, I see why that works, but I don't know what we're doing.
C times.
We're doing calculus essentially,
Yeah, I know,
right?
but what are we trying to solve for?
We're solving for the y component of the velocity as a function of x.
Ew.
Ah.
Frame it. Take a picture.
We better frame that. Okay, next question is, what's the y component? What?
Can I write that on the key outside?
There's no key outside. Well, this is not it.
This is in the review.
Hey, this is the review.
All right. The next question is determine the y component of the particle's acceleration. Well, what's acceleration? Acceleration is dv dt, right? Okay. Got it? Can you do that for me?
Oh, you skipped the
Exactly. No.
Or you could do this. D squared x dt squared.
No.
But you need to, we can. You just need to make sure, you can solve it that way, that'll work. You just need to make sure that the function you put in here for velocity in the y direction, or for, this should be y, right? dy, sorry, dt squared. Just need to make sure that what you put in here for your function is the function with time in it, right? No x's, right? So which equation should I put in here? Should I put in this one?
No,
No.
Which one should I put in?
the y.
I should put in this one, right? Or this one, right?
Yeah.
I should take the derivative of c squared t. So vy is c squared t. When I take the derivative of that, I get c squared, right?
Yes.
Okay, well what if I do it this way? Here's my original equation. I need to convert that into a function of time, right? So I plug in x, and x is equal to ct, right? So I get 1/2 c squared t squared. So that's 1/2 c squared t squared. If you take the double derivative of that, you get c squared again, right? All right.
That's, wait.
Calculus is our friend, except when it's evil. Even when it's evil, it's sort of our friend. We just don't understand it. Okay, now part B. Suppose instead that the particle moves along the same parabola with a velocity whose x component is given by, listen up, Vx equals c divided by the square root of 1 plus x squared. Show that the second particle speed is constant in this case. Whoa.
This all one problem?
So,
Oh yeah.
Oh, it's beautiful, man.
no, the back.
Yeah.
So we still use the same y velocity from the part A?
All right, so that's a good question. Y still equals 1/2 x squared, I believe.
Yeah.
You didn't say otherwise.
All right?
dx dt changes.
Because you're X.
So
So,
x though,
this can't.
Vx equals, no. Sorry. Yeah, Vx, that's what they give us. Vx equals c over 1 plus x squared square root, right? Now, here's where it gets really ugly. I think it's ugly. So we have these two things, given that and given that. We're looking to show that the velocity equals a constant. But velocity is Vx squared plus Vy squared square root, right?
Right.
Okay, we are given that one. We need to find that one. So what we need to find is Vy, which is dy dt. But we have this issue again here, right? So let's do it the fancy way again. This is the same as dy dx dx dt. All right? Where dy, or y, is this. What the heck is dx dt?
VX.
Ooh, that's Vx. Given.
Bam. Finished.
What's dy dx?
X.
That's the derivative of this,
That's X.
which is x. And then this is v, which is c over 1 plus x squared square root.
And that squared plus.
Did you follow that? Because that took me a while to get right.
Well, I got lost.
Okay. If you're lost, you're in good company because I was lost. When I worked this one, I'm like, what the heck?
You're just working it and not knowing what you're doing.
Yeah, pretty much. Actually, you're only seeing my final work through. You're not seeing all the mistakes I made. All right. Velocity in the y direction equals dy dt. But since we have x's going on, we're converting this dy dx times dx dt still equals this, right?
Yes.
We know that dy dx of this equals x.
Yes.
We know that dx dt is actually the velocity in the x direction, right?
That's given.
Which is given. So x times the velocity in the x direction gives us that.
But
It is beautiful, but still perplexing. It's beautiful, but I don't understand
wait,
it.
does that make it constant?
No.
Not yet.
We're not
We
sure.
haven't even finished.
So what is that?
That's just the y velocity.
That's just a y velocity.
Yes.
Then you plug what is constant
That's
beyond
the y
that?
velocity.
Then you plug in the Vy and that in. You square that. Plug that into the V constant Vx squared plus Vy squared. Then you square that.
The y velocity.
Is all you find is what y velocity. You're just and then you're
That's what we just said.
square root
Because we said it's dy dt. The change in y over time is velocity, right? Which equals dy over dx
and then
times
what
dx
is that?
over dt. Those cancel
So you have to solve for Vy and dx. That's Vy, and then you're gonna take that Vy and plug it back in up there.
I'm not an advocate of
And now like
We don't know.
All right, now, you know what? We haven't even finished this one yet, have we?
No.
Okay, so here we go.
You have to simplify it.
dy dx.
Well, what we have to do now is still try to prove that it's constant. So let's get moving. We're almost out of time. Here we go. Vx squared. That means I take that and square it. That means I take that and square it, which is c squared over 1 plus x squared. Vy squared is this and squared. So that's x squared c squared over 1 plus x squared. I square root the whole thing. Now watch this. Pull c out. I get 1 over 1 plus x squared plus c squared over 1 plus x squared.
When I got it,
Oh, sorry, x.
2.
What's that?
Squared. You forgot the X. Beautiful. I see. Hey, no.
Oh, I see. Okay.
What? That's going really fast. No, I mean, I need to.
Okay.
No, I factor Mr. Ruben.
Welcome to Physics C.
Mr. Ruben, don't you factor out C squared, not C?
I factored out a c squared, but the c squared is square rooted. So when I pull it out of the square root, it becomes c.
Okay.
Right?
That makes sense.
Hey,
Perfect
Mr. Ruben.
sense.
So look, it's a constant.
I'm still
Done.
Mr. Ruben.
Yes.
I was still working on the fly, so.
Sorry, out of time.
Yeah, so, Mr. Ruben, next class, we're going to get some from BI.
Wait, sit.
Mr. Ruben.
You're starting to put up. Don't put up. No, Andy, you don't have time.
No, but
Okay, quiet. In this particular one, draw the velocity and acceleration vector. Velocity vector is which way? Okay, still got that 1 point. Which way is the acceleration vector this way?
No way.
If the velocity is constant, there is an acceleration because it's turning. Which way is the acceleration?
Towards the center of the.
Towards the center, because that's a centripetal acceleration. Right? It's changing direction, but not changing speed.